right, we have a special assignment today. I was contacted by an automotive tech student around here in Denver, Colorado, and was asked if I have any videos that provide specifics on the test material that will be coming up for the class. And of course I do have it, but it's kind of spread out over videos on this channel and my paid channel. And rather than try to refer to all these videos, let's see if we can make a video that specifically addresses being able to pass this part of the test. So let's take a look at what we've got here. So I printed this out. We see we want to focus on this area here, which seems to be all on electricity and electronics. I never get asked about performing a brake service or anything like that. It's always on the electrical. All right, let's see. We've got ASE 1020, basic automotive electricity, 2 credits. The ASE 1020, I don't know if this is for actual ASE test, or maybe this is a test in the class that ties in with making sure they can pass this in an actual ASE test. I don't know. I've never taken an ASE test. So understand the basic symbols, letters, and numbers on a wire diagram and ask these. Okay, well, that's pretty general. So maybe we'll look at a wire diagram and look at some of the common things on there. We will have to look at a wire diagram anyway for some of these other things. So maybe we can do that kind of incidentally. We need to define voltage, amperage, and resistance. Ask these questions for follow-up, written portion. Okay, I'm not sure what ask these questions for follow-up, but we can certainly define voltage, amperage, and resistance and explain those a little bit. Use a digital multimeter, DMM, to test for available voltage, voltage drop, and ground side voltage drop. Okay, so we can do that pretty easily. Then we want to use a test light to test for available voltage and voltage drop. Okay, not my favorite way of doing a voltage drop measurement, but we can certainly use a test light to look at voltage drop, and we'll try to set something up where we actually would have a voltage drop that we could detect through a test light. Not really a big fan of the test light for voltage drop because it's kind of subjective as opposed to using the DMM. All right, score an 80% or higher between the written and hands-on assessment. That will be up to the student. All right, then we've got some electronics down here. ASE 2020-1070, specialized electronics. All right, identify all terminals of a relay using a test light or DMM. All right, so that could be interpreted a couple ways. It's a little bit hard to use a test light to identify the terminals on a relay, but we could identify them a lot easier in the relay port for sure. So maybe we'll try to see where we can apply both. We want to use a test light or a DMM to identify all terminals of a relay. It sounds to me like we're supposed to do that on the relay itself, which is far easier to do with a DMM than a test light. So yeah, we'll probably do a little bit of both on the relay itself and in the vehicle's relay port itself. That'll also offer a little bit better understanding either way. All right, disassemble and reassemble terminals in an automotive electrical connector. That sounds like repinning a connector. That's going to be a mechanical thing. So they should be able to do that. I'm sure they'll have some kind of like lab session or something where they'll do that. Measure the waveform of a high side driver controlled output using the picoscope. Well, that we can certainly do. And then we want to measure the waveform of a low side driver controlled output using the picoscope. We can certainly do that as well. Might be a little challenge finding a high side controlled driver. Most drivers are low side controlled, and we will also explain the difference between those. So we may have to look at a wire diagram to try to find a high side driver. What would be, I'm trying to think what would be high side controlled. Yeah, the high side driver controlled output. So that means we can't do something like just turn the ignition switch on or the lights on or something. Even lights are usually ground side controlled. But with the controlled output, we're looking for something that is pulse width modulated by a computer. And those generally are low side controlled. So we'll have to look into that. And that's all we've got to do. Okay, so where do we want to start? Let's start with defining voltage, amperage, and resistance, because that's going to be the starting point for a lot of these other things. Okay, my assumption is that the students in this class would have definitions provided to them that probably they have to memorize or whatever, but these are going to be my definitions mostly. The important thing is to understand the definition rather than just rote memorization of the definition. That's what we're going to try to do here. So voltage, I think of voltage as a pressure. I always use water analogies, which we'll do when we explain the difference with these in a visual way. A water analogy, in my opinion, is the easiest way to do this. So I think of it as pressure from whatever the power source is in the car. It's usually going to be the battery, right? That pushes current, pushes electricity through the circuit. And we'll explain that. Amperage, it's important to understand a lot of people use amperage and current interchangeably. Amperage is a measurement of current. So when we talk about amperage, we're talking about the measurement of the current. Current is that flow of electricity through the circuit, specifically the flow of the electrons through the circuit. And the amperage is that measurement. An amp is a specific measurement, and in my background there's a couple of fancy numbers that are burned into your brain forever. One of them is Avogadro's number, 6.02 times 10 to the 23rd. Another one is going to be, I don't know if these guys are getting into coulombs and getting really specific, but this is going to be 6.24 times, I think it's 10 to the 18th electrons per second. So an amp is going to be 6.24 times 10 to the 18th. I don't know what that's like, billions and billions and billions. It's a bubble butt billion electrons that are going through every single second. And that is the actual measurement that you're doing with amperage. Current is, of course, just the flow of electricity. So in a high amperage circuit, you may have way more than this going through per second. And a lot of that is going to vary on the resistance, the final definition. Resistance is the obstruction to your current, and that, of course, is measured in ohms. So anything that inhibits or impedes that electrical flow, that is going to be resistance. Now, there's a relationship here between these, as you know, with Ohm's law, where V equals I, amperage or current will be I in this formula. Voltage equals your amperage times resistance. So if you're any good at math here, you can see that the relationship would be the higher the resistance, the less the flow. The higher the resistance, the higher the voltage. The more flow that you have, the easier that the electricity flows through, the less voltage you would have. Higher current, less voltage, because you've got less pressure built up, you've got easier flow. It's best explained through a water analogy, so let's go ahead and look at that real quick. Okay, so typically what I'll use is like a water tap, a water faucet. We've got water that would come through here, and this is going to be your voltage. This is going to be your source for your pressure. And then let's say we've got a hose. Let's make the hose a different color. I'm going to draw this a little bit better here. This is our faucet handle, and then we've got water. We're going to put the water in blue, actually, so the water flows out here. And then we've got a hose that we will put in pink here. All right, and of course the water can flow through this hose. Now, if we cap off right there, and we block this faucet so no water can go through the hose. In the case of like a car battery, we're going to have 12 volts, all right? So that's kind of our maximum voltage, our maximum pressure. Now, if we open this, well, now we, of course, have water flow through, but of course, now we don't have that buildup of pressure here because now the water can flow through. Think of it, if you block with your thumb you have a really hard time holding that water back from the tap. You're creating a resistance in doing that. So you're building up pressure behind your thumb, and you can feel that pressure. Now you let that go, and now there's no more pressure here. So actually now, at least as far as at this point, you would have zero voltage, zero pressure, because now we've got flow. Again, increasing flow lowers the pressure. Now, we can also add a resistance here. Let's say that we put a kink in the hose here. Like we step on the hose right here. Okay, well now, as you know, this creates a totally different dynamic. Originally, we would have water flowing out of the hose at a pretty decent rate, but now you know that the water flowing out of the hose is going to be pretty much a trickle, right? Because we've impeded or resisted the flow at this point here. Now, what does that do here, though? What happens here? Well, here, of course, we've built up pressure at this point. Now, that means the pressure at this point and this point are going to be the same. Actually, the pressure at any point here is going to be the same before the obstruction. Now we do have some flow here, so we're not going to have 12 volts there, but maybe it'll be something like 11 or 10. But we built up pressure. Now, of course, as soon as we release this kink in the hose, well, now we no longer have that obstruction. Our flow returns to full speed, but we're going to drop our pressure. There's going to be no pressure in here again. All right, let's step on that hose one more time. You know, and just visualize this with thinking of if you've ever played around with a garden hose, right? You want to stop the flow of water on the hose. What do? You bend the hose or you pinch it or something, right? That's going to build up pressure behind that kink. All right, so that's going to be your resistance. Now, there's going to be one thing that's going to be very interesting here, and this is a very important concept to know, and that is we've now lowered our flow. We've lowered our current. The blue is going to be I, current, right? The current is going to always be the same throughout the whole system, okay? So if we slow this flow here down to a trickle because we've obstructed the hose, well, that means we slow everything up here down to that same trickle. You can't have a really high flow here, but a really slow flow here. That's impossible. It all has to flow the same. And that's a very important distinction to understand in electrical circuits. We can see here that as we've increased the resistance here, we have decreased the current, but we have also increased, now our voltage is going to be a lot higher. We've increased the voltage, right? If we completely close this off, completely block it off, well, now our current, of course, will be zero because we've totally eliminated current. If we have complete resistance, if we have infinite resistance, by blocking this off, we will have zero flow through there, no amperage, and of course, we will have the full voltage. Again, increasing resistance, decreases flow, increases the voltage. I want to make sure I point out one other thing. This is actually one of the most important concepts you need to understand if you are ever going to understand doing electrical and electrical testing and things, and that is understanding the voltage drop. So that is not one of the definitions that we had here, but we need to measure voltage drop as part of this assignment. So it's going to be essential to understand the voltage drop. So a very, very, very important concept here. Okay, so we've got our original voltage source from the battery, or in this case, our faucet, 12 volt source. And we've of course got this resistance right here. All right, so we know prior to the resistance, we obviously have built up some pressure, right? If we pinch that hose, we build up the pressure behind it. We're going to say that that voltage is, let's say, 11. It's not going to be 12 because we haven't totally closed it off. All right, now, very important question, one of the most important questions you need to be able to answer without even hesitation for electrical. What is your voltage here on this side of the kink in the hose? What is your voltage there? You should, without hesitation, answer the voltage is 0. There is no voltage there. Now, what is the current here? Well, we could calculate that actually if we had any two components of our Ohm's law, V equals IR. But we do at least know whatever the current is here is the same anywhere in our circuit. It's the same current, but the voltage has dropped here. After a resistance, no matter how much resistance there is, after that resistance, the voltage will be 0, unless, one exception to that, unless we introduce another resistance. Now, in this case, all right, so now we reduce our flow even further because we've got this second resistance. We will have a voltage here, maybe it will be 3. Now, there's also Kirchhoff's law that all of your voltage drops must add to the source voltage. So if that voltage is 3, that means this one here is going to have to be 9 so that it adds up to our original source 12. But after this last resistance, what is our voltage here at this point? It's going to be 0. All right? Now, by adding this extra resistance in here, another kink to the hose, we've restricted, again, our current. The flow will be even less, and the effect of that is going to be throughout the whole circuit. So it's not like we maintain the flow we originally had. When we pinch that second part of the hose, we lower the flow for everything. Again, think about it. How can you have a faster flow anywhere along here if you have a slower flow here? It all has to be the same. The current will be the same before or after a resistor. The voltage will not. So hopefully that explains the definitions part, maybe a little bit more thoroughly than needed, but the understanding is going to be essential to know how we do some of these other things that are asked on this test. So let's go ahead and see what we've got next. All right, that was our definitions. We also used a couple of abbreviations and symbols there. Let's draw that in more of a diagram form, and let's use at least a couple of basic symbols that will apply to our definitions. Okay, so let's look at a very simple circuit diagram here. We've got a battery here. I forgot to write that. This is generally a symbol used for battery. You're going to be able to tell with the plus and minus there, whatever symbol is used. Sometimes they actually draw a little box that looks like a car battery. The wavy line, of course, a fuse. This would be a symbol for a switch. Right now the switch is opened. This battery is 12 volts. What is our voltage right there, by the way? What is our voltage right there? It is going to be 12 volts. All right? It's like a hose that we capped off because the switch is open. All right, on the rest of this, we're going to use this symbol here. This is going to be a motor, and this is a pretty universal symbol for a ground. As you can see, if we close this switch and make contact, we would run this motor, right? Now, here's a question. If we were to look at our voltage right there before the motor, I'll give you a hint. A motor is a, think of it as a resistor. It's a load, to be technical. Before or after a resistance, before or after a load, Same impact with our Ohm's law thing. What is our voltage right before the motor? Again, a hint, think of the motor as like a kink in the hose. That's going to be 12 volts. What is our voltage going to be here after the motor? It's going to be 0 volts, provided we have a clean ground, all right? Now, we can substitute in, instead of a motor, pretty much the resources that I use if we have a light bulb. That symbol there is the symbol I will see in most of the diagrams I reference as a lamp. Let's also introduce something else here. We're going to put this symbol in here and then bring that to our ground. This symbol here is a resistor. Obviously, in this situation here with our switch closed, we would light the lamp, but because we have a resistor, it wouldn't be at full brightness. We can also have this symbol here, which means a variable resistor. And basically, by how we set a dial or a lever or something, we would have more or less resistance, which would increase or dim that lamp. So that's another pretty common symbol. This switch that we have here could also be replaced by something that usually looks like this. And this is going to be a push button switch, one where you push the button, as opposed to a flip the lever switch. All right, another common thing, let's say that instead of a switch, we were going to have a computer control this thing. So first of all, this wouldn't really be realistic. This is just to show the symbols. It wouldn't be placed here, most likely, in this diagram. But we could also have a transistor. Usually looks something like that. Now, the transistor has 3 parts. The transistor, I usually think of it like a push-button switch. So this is going to have to go to some kind of thing like a computer that's going to control this. So we're going to have a base, a collector, and an emitter. And basically, if we input a signal here, and it depends on the design of the transistor, we can also have one where if we provide a ground to this base, but either way, it's going to activate this transistor and act like a switch to continue current through here. Transistor also, sometimes I've seen it drawn a little more square looking, maybe something more like that as well. But again, symbol for a transistor, something that I would imagine you're going to have on your test. Okay, another thing we could do is maybe instead of the lamp, and actually this would pair well with a resistor being in this circuit. So let's get our resistor back here. All right, that's our resistor. All right, this is going to be a diode, but this in particular is going to be a special diode. That symbol there will be a light emitting diode, an LED. And a diode only allows current to go one direction. It will not allow current to go backwards. In certain devices like an alternator, it is possible for current from the battery to go back through the alternator. We don't want that to happen. We only want it to go from alternator to battery. So we would have a diode in there so that electricity can only go one direction. A diode will always need to be used in conjunction with a resistor, otherwise it's going to burn out. So this actually kind of makes sense here. All right, but the diode and the light emitting diode, I have to imagine, is going to be a symbol you would be expected to know. All right, we'll see some other symbols as we will have to look at a real wire diagram in order to be able to do some of the things we're about to be asked to do with the DVOM and the picoscope. All right, so we've done some basic symbols and annotations. We've done voltage, amperage, and resistance definitions. We now need to use a digital multimeter to test for voltage, voltage drop, and ground side voltage drop. Okay, so first of all, let's look at what we're going to be doing. All right, so we're going to have a battery here, and we're going to have a cable from the battery, and we're going to go to some kind of device. Where are we going to measure? So we want available voltage, voltage drop, and ground side voltage drop. So we're going to want to have some kind of device here. Ideally, I think we would have a light bulb, right? And then this is going to go off to ground. And what we want to do is we're going to want to take our DVOM here. Let's draw that in a different color. All right, we're going to use our DVOM. Actually, these guys are calling it a DMM, digital multimeter. That's fine. We'll use that. We would have a readout screen. We're going to have, of course, 2 leads off of it. We're going to have a red lead. We're going to put that there. We're going to have our negative lead. We're going to put that there. That's going to measure our available voltage. All right, we measure just right at the battery. Let's see, then it wants us to measure voltage drop. Okay, well, it's a good thing that we discussed voltage drop, isn't it? Because we can look at this diagram and we know exactly how we would do that. At least I hope you do. All right, whatever this device here, it doesn't matter. It's going to be a load on the circuit. You always have to have a load on the circuit. Remember, if we didn't have a load on the circuit and we just did this, again, this is connected up to our battery positive. Well, what we would have is the battery positive directly to a ground with nothing in between. You guys know what happens when you do that. You short circuit and you're going to melt this wire, right? So you always have to have a load in there. We will go ahead and keep a light bulb in here as the load. And we know that the voltage drop is going to be very easy to do for this assignment. We're just going to take our positive lead, put it there. We're going to take our negative lead, put it on the other side of the circuit. What's our voltage before the resistance? It's going to be 12.6 actually for the car battery. What's our voltage going to be here? It's going to be 0, right? Our voltage drop is 12. We will see 12 on our meter. We will see the voltage drop across that light bulb if it's turned on. Now, actually, it's kind of interesting in this case. If this light bulb happened to be burned out here and the light bulb wasn't functioning, we would actually still see the same thing because, again, we've got an open here. We've blocked off. If the filament in the bulb is broken, well, we've blocked off. That means we would technically have 12 volts right there at the break in the filament. We would have 12 there. This is still connected to a ground on this lead of our meter. We would actually still read 12 whether the bulb is lit up or not. But with the bulb lit, we're technically measuring the voltage drop. It's very important to discern that what we're measuring in the open here is not voltage drop. We're measuring difference in potential. With the bulb actually connected, we are indeed measuring voltage drop. Voltage drop only happens when you have current. If you do not have current, it is not voltage drop, all right? Okay, and then we've got one last thing we want to do, and we want to measure the voltage drop on the ground side, okay? We can do that. We'll need to find a device, and then that's going to go off to our ground. And what we want to do is we want to measure the voltage drop on the ground side. Now, should be pretty obvious to you that we should not have any voltage drop on the ground side of a circuit. So in other words, again, if we measure, this light bulb is lit up here. If we take a lead and measure there, we take a lead and we measure there, what are we going to read on our meter? We're going to read 12 volts, right? By the way, if this bulb is lit, that means we have amperage through there. Is our amperage here after the bulb different than the amperage before the bulb? Absolutely not. Amperage is going to be the same through this whole circuit. So just a reminder there. All right, now, if we were to take our positive lead and we were to measure for voltage drop on the ground side, well, if we measure there and we take our DVOM and measure here, what should we read on the meter? All right, well, ideally, we know that after the resistance, we should have 0 volts after the resistance. We'll have current after the resistance and before, but we will have full voltage drop after our load, after our resistance here. So that means if we read 0 here, well, it should be 0 anywhere along here. That means we also have 0 here. The meter reads the difference between what you see on the positive and negative lead. 0 minus 0 is 0. We should read 0. Now, why would we want to do this? Well, what I believe your instructor is trying to do is show you if this bulb is not lit up as bright as it should be, one explanation for that could be that you have a resistance in your ground, which is pretty common, and very often that resistance is going to be where the ground actually connects. If you have a ground to the frame of the vehicle, for example, that's very often where you'll find this. Well, if we have a resistance here, remember what we mentioned earlier. See, it's all coming back together. We're going to have some voltage here in this area, but again, we will have 0 volts after the resistor. So if we measure anything on the meter now, let's say we measure 2 or something like that, that's telling us we have to have a resistance between these 2 leads. We should not have that on a ground. A ground should be clean. So that's what they're asking us to do. So let's go over to a car and see if we can do it for real. All right, this first part is going to be very easy. We're going to take our meter, we're going to look, oh, that would have been another good symbol to know, by the way. All right, so if we look over here, we've got our volts with our solid line and dashed line. That's going to be DC volts, AC volts, which we typically don't use very much in automotive until you get into some more diagnostics, like with alternator or whatever. That's going to be the V with the wavy line. So we want to go to a 20 volt scale here on our meter to DC volts. Set our meter up there. We've got negative terminal on the battery here. We've got positive terminal on the battery here. And we can see my battery is a little bit weak because I haven't driven this car for the winter much, but we're holding 12.05 volts. We've now measured our source voltage. Okay, the next thing it wants us to do is to measure a voltage drop. So in order to measure a voltage drop, the first thing we know, we have to have current. We need to turn something on. The first thing that's coming to mind for me is probably a headlight. All right, if I look here, we've got a 2-wire headlight connection right here. Now, the only thing is this car has pop-up headlights, so I may not be able to access it if we pop the headlight open. I think there's a way I can turn the lights on, though, without popping the headlights. So let me give that a try. Okay, it actually worked. We can see if we look real careful there, we can see some light from the headlight showing through. So the headlight is on now. So I'm going to measure voltage drop across my headlamp bulb. So what I'm going to do is take 1 lead of my multimeter. Let's get the multimeter in there. All right, now the easiest thing to reach is going to be here, this brown wire and this black wire here. So we want to probe those. Of course, one of those is a power going into the bulb. The other one is the ground returning from the bulb. So one of them is going to have 12 volts. The other one should have pretty darn near 0 volts. Now, which one is the power and which one is the ground? Well, there's several ways we could look that up. One of them is a wire diagram. The other one is we can take my negative lead for my DVOM here, and I'm going to connect this to battery negative. Then I'm going to take my positive lead here, and I'm going to touch it to the terminal on the brown wire. All right, we see, yeah, my battery's getting really weak here. We read 10.41 volts. Now, this is a little bit off the point here, but one of the things is there's 2 explanations. My battery's really, really low, or I could have a voltage drop on the positive side of this circuit, but we've determined this is the positive side of the circuit because we're measuring against the ground and we're getting 10 volts here. If I measure the black wire, I should have nothing, and I see nothing there. So that means the brown is positive, the black is negative. Let's follow the instructions that we were given. We want to measure the voltage drop across our bulb. So what we're going to do is put our positive lead where we know the positive was, the negative lead on our ground there. All right, and we see we're measuring 10.05, I saw, a little tricky to get here. 10.06. All right, so we've measured voltage drop across that bulb. Now, one of the things is we also know from the fact that our reading was positive, it read 10.06, not negative 10.06, that our polarity or our direction of negative and positive was correct. Another way we could have determined is the brown wire positive and the black wire negative is the fact that we saw a positive reading. If I switch around and I put my positive lead on the ground, my negative, well, not the ground, we don't know it's the ground yet. My positive lead is going on the black wire, whatever that is. My negative lead is going on the brown wire. All right, we see we now get a negative 10. What that means is my leads are reversed and the positive lead from my DVOM is on the ground. So that's another way I can identify my wire colors here. All right, the other direction, let me just reread this. All right, measure the ground side voltage drop. Okay, first of all, do we have a voltage drop problem on our wiring? So one of the things I'm a little worried about is that the voltage that we measured at the bulb actually is pretty different than our source voltage. And it really probably shouldn't be that different. So I'm going to go and, so I'm going to measure my battery voltage at my positive and negative directly from the battery. We see we have 11.27. All right, so my battery is a little bit weak, but the problem is that we measured 10 something at this bulb, which means we're losing some voltage somewhere. All right, we had 11.27 at the battery, we're reading just about 10, so we've got almost a little over a volt of drop from our battery voltage and where we're measuring at our light bulb. Where are we losing that volt? Well, what our directions say is we want to check the ground side, okay? So we can totally do that. We're going to take our negative lead, and just like we showed, we're going to go over to our negative side of the battery. On one lead, the other lead we're going to put on the negative for our point after the bulb. There should be no voltage there. And as we can see, we only have 0.13 volts. That's pretty acceptable. All right, that's pretty minimal. So that's certainly not where we're losing voltage. We're probably losing it on the positive side, aren't we? So to do that, we're going to do a little extra work here. Since we have an actual voltage drop application going on here, I'm going to take my positive lead and I'm going to put that on my battery positive. And I'm going to take my negative lead and I'm going to put it on that positive wire, and we're going to measure the voltage that's dropped on this positive wire. And there it is, 0.91. So we are losing almost a volt. By the way, did you notice Kirchhoff's law again? If we add up our 0.91 and our 0.13 or whatever, it actually adds up to the exact voltage drop that we measured. The sum of all voltage drops will equal the source voltage. So on this car, I really do need to replace the wiring for this headlight on the positive side, if nothing else, but we are losing a volt on the positive side. All right, let's see how our progress is here. Let's see, we used a DMM to test available voltage, voltage drop, and ground side voltage drop. We also tested power side voltage drop and found voltage drop on a power side. How about that? Okay. Use a test light to test for available voltage and voltage drop. All right, this actually will be a pretty good lesson because you're going to see that this is not going to work out quite as well for doing the voltage drop assessment, but it is a good way of identifying circuits and being able to determine that we have voltage. So let's grab a test light. All right, for the test light, same thing as the DVOM, honestly. Same exact thing. Instead of a digital readout, though, we're just going to get a light up. And pretty much I use this more for a qualitative or a yes or no instead of a quantitative, which is how much, because it's a little subjective. But we can see we can check our source voltage by going from the negative to the positive. We're essentially just lighting up a light bulb here. We see the light bulb lights up fairly nice and bright. Now, one of the things that I like with this is another way we could find out. Was our positive on the brown wire or the black wire? Well, let's see. My test light is connected to a ground. My test light is on ground. That means if I find a positive, it will light up. So let's go over to the black wire. Doesn't light up. There's not a positive there. Go to the brown wire. We see it lights up. All right? Can also reverse that. I could take my test light and make a ground finder out of it. Take my test light, put it on battery positive. Now, anytime my test light finds a ground, it's going to light up. Let's go over to our positive wire. We see there's no ground there because that's a power. Test light does not light up, but if I go over to the ground, we see it lights up. Okay, now let me reread these directions just to make sure. Okay, it does say it wants me to use the test light to check for a voltage drop. All right, not my favorite thing to do, but all right, so what I'm going to do is put my test light over to the negative. We're going to look at the intensity of our test light there because that's our source voltage. All right, that's the brightest that it's going to possibly be. So we're going to kind of memorize that a little bit. All right, we're going to move that over to here. And the thing is that it should show a little bit dimmer, and maybe it does. Let's try this. Let's try turning the lights out. Okay, we are going to compare that intensity to that intensity. I don't know about you guys. I don't really see the difference there. I could definitely see it with the multimeter though. But this is testing a voltage drop with our light. You know what? Maybe it is a little less intense. Take a look there. I don't think so. I don't think I can notice a difference. Okay, if you did notice a difference in intensity where there shouldn't be one, you probably have a fairly significant voltage drop. All right, let's go check our progress again here. All right, we have used a test light to test the available voltage and voltage drop. You really see the advantage in learning how to use a DVOM. Now you got to score an 80% or higher between the written and hands-on assessments. Hopefully you guys will be able to do that. So now we can move over down to here for our specialized electronics. Ooh, it's specialized electronics. Identify all terminals of a relay using a test light or DVOM. We will obviously do both. So first of all, we need to understand the terminals on a relay, and I'm still a little unclear on exactly what they're asking here, but let's take a look. All right, if we are going to identify all the terminals of a relay using a test light or DMM, we have to know how a relay works, so we all got to be on the same page. So, new symbol, I guess, too. So relay, your symbol for a relay is going to either be a box like this, and it will have various wires coming out of that, and typically it'll have like a, I don't even remember what the numbers are. There's like an 86 and an 87 and an 86A, whatever. There'll be, I'll put X and Y there. There'll be different designations on the terminals. Most relays will also have a little map on the back of the relay, which is going to be very helpful if you're going to be allowed to use the relay map. That's going to be very helpful. Not all relays have a relay map, so you either need to be able to read a diagram or, like I often do, just be able to figure it out with your DVOM or test light. More often, you will find the relay has a little more specific symbol, which is actually quite a bit more helpful. And the relay is going to have a symbol that looks something like this, with a terminal here and a coil, and you will have a switch here. And of course, we've got wires that will come off this way in our diagram. And you will also have designations here, and I don't particularly remember what they are. We'll see it when we look at a relay, but you're going to have something like a, oh gosh, let me think. You may have, I know that you're going to have like a 30 on the load side here. So you may have like, I don't know, 85 and 86. And then the number here would be an 87, I believe. You got like 85, 86, 87, and 30 generally on most relays, like a GM or something. It's not so important the designation of the numbers, although that's a really foolproof way of going if you're looking on a diagram. It's more the function of the relay, again, that's the most important, especially if you don't have a relay map and you need to do what we're being asked to do in this assignment. You may also have another thing off here where when this switch is open, it's actually not open. It's actually connecting to something else. And then when you activate the relay, you pull that switch down to this connector and now run this circuit instead of this one. So you can also have that as well. We'll just make this very simple. Hopefully they don't throw a curveball on you. But we're just going to make this very simple. All right, this side of the relay here is the control side. This side of the relay here is the load side. On your typical relays, what you're going to have is you will have a positive feed into the relay, and generally you get a ground side control. So somewhere here will be a switch that goes off to ground, and the operator of the vehicle will do something to close that switch. Maybe this is for headlights. Let's say this is for the headlights. So when I turned on my headlights, what I did was I closed that switch. Well, there was already a fused power feed here. So I've got power coming here, through here. When I have that switch open, what's the voltage? If I were to measure right there, what's the voltage right there? It's going to be 12 volts. So actually, anywhere along the circuit right now, 12 volts everywhere along my control side. Now, I'm going to go ahead and turn my headlights on by flipping the little switch on my dashboard. What is my voltage here? Still going to be 12 volts. What is my voltage here before this coil, which is actually an electromagnet? That's going to be 12 volts. What is my voltage here after the electromagnet? It's going to be 0 volts. Remember, we get full voltage drop across the load as long as there's no other resistance. That means at our switch here, which is now closed, also 0 volts. We now also have current going through here. And what this does is when we now have current going through here because we've closed this switch, 0 volts there, that creates a magnetic field. That magnet operates on this metallic switch to pull this metal switch closed. And now with the relay active, we now have continuity or connection on our load side. Typically the load side will also have a full-time positive, but then it's going to go to something, in this case our headlights, which will then go off to a ground. When we turn off our headlights by opening this switch, we now, of course, well, actually we'll still have 0 volts here on that ground. That changes to 12 volts. We no longer have current going through here. That means our electromagnet no longer operates and our switch opens here, which means we no longer have current going to our light bulb and the lights turn off. All right, so again, we've got a lot more detail under diagnosis and understanding of relays on this channel that will explain this a lot more thoroughly. But given this, we now know what we want to do to look at this testing. One of the challenges that we can have is it's not uncommon. It's going to be very easy to find the control side on a relay, even just with the relay itself, because this coil here, we're going to have continuity on that coil side. We will be able to see that with the meter. as opposed to the load side of the relay where there won't be continuity. So by using our DVOM in a continuity mode, we will be able to look at the relay and tell the load side and the control side. But the challenge is going to be, we need to find, right? We need to find the individual terminals. Okay, that can be a little bit challenging. So, for example, one of the challenges we can have is if this is a full-time positive over here, and this is a full-time positive over here, well, without a map, it is kind of hard to tell in the car where your load side and control side power sources are. Now, a lot of cars, you're going to have a full-time load side power here, but this control side power will actually be controlled only when the key is on. So you may always have power here, but this is going to be powered only on key on. Now, not all cars have that. So we'll have to use a little creativity with our understanding of the relay to identify all the terminals on the relay. Now, technically it says identify all terminals of a relay. That means we would determine the terminals on the relay itself. I kind of think this may also indicate that we want to find them in the car, in the relay ports. So let's do both. Let's do it both ways. I mean, we kind of, it seems to me we've got to do this both ways because we want to use a light as well, a test light. And if you're going to do it with a test light, you have to do it with the car. There's no other way. You're not going to use a test light on just a relay out of the car, right? There's no power there. So let's try to answer this thing so we make sure we pass. All right, we're going to go over to this car while mine charges up. There's cooling fan high, 69. Looks like maybe this one right here. Okay, so let's pull that out. And if we look, we have a map on it that looks very suspiciously like what I wrote on the board. So with this, we don't need anything. We can identify the terminals of the relay. We see our control side here is 85 and 86. Did I draw that on the board correctly? Oh, I did. Hey, how about that? So we see our control side is terminals 85 and 86. Our load side is going to be 30 and 87. We see when that switch closes, we would move the power from 30 to 87, or maybe the power is from 87 to 30. And if we look on the bottom of the relay, a little bit hard to read. I don't know if the camera's going to pick it up. But I can see 87 here, 30 here. 87 and 30. That's these two. So these are our load side contacts, 87 and 30. That means 85 and 86 will be our control side here. Here's another thing I can do to cheat just a little bit. If we look really carefully, our control side are not as thick and wide as our load side. And that's because you use less current on your electromagnet. On your control side, you use low current here to control a higher current circuit when we close that switch. So we can just look at the relay and I can tell you that these points here on 85 and 86 are definitely thinner and less wide than our 30 and 87. So these are definitely load side. All right, now we can use a DVOM as well to check this. All right, if we go to the diode mode, we should detect any kind of continuity regardless of our resistance pretty much, so we're going to go there. The other thing I like about it is we're going to have an audible signal. If we have continuity in a circuit, the meter is going to beep. All right, so we could actually do this without a map, but we have the map, so we have a little bit easier time. But we know that 30 and 87 are going to be open. It only closes when the relay is energized. That means 85 and 86 with our coil, we see that that is not open. There is continuity. There is at least some connection there, even though there's going to be a fairly high resistance. So if we go over to 85 and 86 here on our control side, there should be continuity. All right, and there is. It's not enough that our sound went on. Sound only goes when you've got complete continuity, I believe. We see we've got 76 ohms. We could have very well set this on our 200 ohm scale and it should read about the same. So whatever the case, we have continuity on that side. That means on the other two terminals, we should not have continuity. And you see we do not have continuity there. So that identifies that our load side terminals are these two, our control side terminals are these two. Now, what we don't know is where our voltage source is necessarily coming in for either the control or the load side. That we will have to go into the car for. Okay, for what we're going to do now, I think we'll start off using the DVOM. We're going to be looking for voltages now. So what I'm going to do is, and there's different ways we could do this. Of course, we could look at continuities through a ground or something. I think this will be the easiest way. Again, we need to just identify these terminals. I don't think it matters how we do it, right? As long as we identify them. So I'm going to go to a 20 volt scale there. I'm going to look for voltages here. So what I'm going to do is take my negative lead. We're going to put it to, you can put it either to battery negative or to a ground anywhere. And I'm going to use this bolt that's sticking out of the frame of the vehicle. This post right here happens to be a battery positive. It's for having easy access for jumper cables. If I touch that, we should get battery voltage. We do. So that means if I find battery power with this lead, we know we have a voltage source. Now, as I mentioned earlier, a lot of times, not always, but a lot of times, your relay will be set up here so that on your load side, one of your load sides will have power at all times, whereas on your control, you will only have a power that comes on with the key on or the engine running. So maybe this car is like that, we'll see. We know we've got 87 and 30 here. So if I line my relay up into the port, all right, so that means 87 and 30 are these top and bottom ports. 85 and 86, the control side will be these ports. So I'm just going to stick my probe in here, and that is a power. If we see we found power at all times on this port, we don't even have key on here. This means we can be very specific now on identifying the terminals of our relay. My meter probe is in the terminal for 87. That means if we look at our map here, 87, terminal 87 is where our power source comes in. That means 30, when we close the switch, is where the power will go down. If the relay is energized, this is our 12 volt power source pin, number 87 there, and 30 is going to go to whatever the load is. I already forgot what it was. I think it was a cooling fan. This also means, by the way, because we have power there at 87, because 30 would be where the switch would close to move that power to the device, if we were to jump 87 and 30, we would power that device. Let's go ahead and do that. All right, I am very, very, very sad because for as long as I've been making videos, I have always had the same paper clip that I have used for almost 9 years now that I've been doing this stuff, and I lost it. I left it in someone's car. So I had to get new paper clip, but you can only buy them in groups of 500, so it's no longer special to me anymore. It's very, very sad. All right, what I'm going to do is jump 87 and 30. We hear, we get the fan to operate. Basically, we acted like the relay there. All right, now very, very extremely important. Do not ever do that unless you know exactly that you are on the load side. If you do that on the control side, if we do that on the control side, we would be bypassing the load. We would create a short circuit. We could permanently damage that circuit. If we're lucky, we blow a fuse. If we're not lucky, we might blow a computer. All right, now the other question we had is there power at all times on the control side? Well, very easy to find out. I'm going to take my DVOM. We're going to test this point of the control side. Nothing This point of the control side, nothing. Okay, so this is very easy to identify. We are only going to have power come to the control side with key on in this vehicle. Let me go grab a key. All right, I'm just going to leave my meter there. Turn the key to on. We did not get power. That means it's going to be over on the other side. All right, little trouble. There it is. Okay, so that corresponds with this pin on our relay. That says 86. That means 86 is here. This is the power source pin for our control side. The user of the vehicle will need to do some type of ground side control, turning on the AC, whatever it is, in order to complete the circuit through our control side, activate that magnet, and then pull our switch closed here. Okay, can we do this with a test light? Absolutely we can. It makes no difference, especially in this case, it really doesn't, because we just need qualitative result. We just need to see, do we have power, do we not? We don't really care how much. I'm gonna take my test light, hooked it up to my ground or battery negative post, whatever you prefer. When I find a positive, the test light lights. We can do the same thing. I'm going to go ahead and test in here. Whatever this is, I don't even know, right? You don't have to necessarily do this with the map. Nothing's there. I put it here. We have power there. All right. I know either that's going to be a load side or a control side power. Now what I'm going to do is test here and here on the other two relays. Neither lights up. I'm done right there. I know this is going to be a load side power on this particular vehicle here. If one of the other relays lit up with my key off, well, then it's a little more challenging. Then you got to do a little more research. This car, it's easy. That is a load side power. To be honest, I can actually look at the slots here and I can see the one directly opposite is the same size. The other two slots are thinner. That means opposite that is going to be my load side towards my device. All right, now let me turn the key on. All right, now with key on, I can go over to my control side. There it is, lights up right there on my first try. So we can see that now we have identified our control side power. The other side of the control would be the ground side on the control. All right, let's check our progress here. Identify all terminals of a relay using a test light or DMM. We actually did that and then some. We identified all the terminals of the relay itself. We also identified the relay ports in the vehicle. We even verified it with a bypass test. All right, disassemble, reassemble terminals. That I know they are probably trained on how to do that and have tools to be able to repin a connector. I believe that's what that refers to. We only have two more things to do. We need to measure waveforms on a high side driver controlled output and a low side driver controlled output, both using the picoscope. Well, that is what we do a lot on this channel anyway. So we will go ahead and cover that. One of the things we want to do, I need to find a high side controller. So we may look at a wire diagram in order to do that. But before we do, we need to make sure everybody is on the same page and we know what high side and low side control even means. All right, high side and low side control. What this is referring to is the instructor in this class wants the students to identify a ground side or positive side computer controlled, most likely pulse width modulated device, and then look at the square wave on a pattern with the picoscope. So in other words, we're going to have something, we need something like this. Most things are controlled with a ground side. Let's first of all differentiate what that means. So we're going to have PCM here, all right? And we can have this a couple of different ways. Let's make like a really simple one. There are so many designs of this. It's crazy, but let's make one a little more familiar to us. We're going to have a battery here, and then we're going to have a, oh, I don't know, what's something that we're going to control? Fuel injector, probably, right? Fuel injector, coil. Let's do a fuel injector. I don't know if there is a electrical symbol for a fuel injector, but this is going to be mine here. Fuel injector is going to have a little coil. It's almost like a relay, actually. Solenoids are very similar like that, where there's going to be a magnet here and there's going to be a little pintle here. And by turning this magnet on and off, we open the pintle and close it, open, close, let fuel either go through or not. And we sort of pulse that through control of this magnet. Now, the control of this is, in every vehicle I have ever seen in my life, going to be ground side controlled. Did he use pull down? No, low side driver. Okay, so there's different terms for this: ground side controlled, low side controlled, pull down. All of these refer to the fact that obviously you can see we're going to have a switch here. That's going to go to ground, right? And we're going to have our current that goes through this injector when this switch is closed. No current goes through it when the switch is open. And the opening and closing of this switch, we will notice, is on the ground side, not the power side, right? Now, even though this here is the ground side, with our device in this particular state, what is our voltage right there, right now, with this switch open on this injector? That is 12 volts. What is our voltage here on this side of the injector? 12 volts, right? It's like water pressure. The water can't flow. So it goes here, it's filling up our coil, it goes here, but it stops right there. It's like a hose that's capped off. So the pressure is the same all the way through. What is our current through here? How many amps here? 0. No amperage, no current, because there is no flow. Now, once we complete this switch, now everything on this side of the circuit, 0 volts. It still stays 12 volts on this side of the injector at all times, though. That is going to be very important for us to understand, because if we do not hook up our picoscope correctly, and we only measure on this side of the circuit, we are always going to measure 12 volts no matter what. We need to make sure we understand this concept, because our 12 volt or 0 volt, whether we open or close this switch, will happen on this side, the ground side of the injector. Now, this control here with the switch, unlike what we've been playing with before, this is going to be controlled inside the PCM. The PCM is going to control opening or closing that ground on this injector, and it's going to do that very, very, very rapidly, right? So that's why we want to use the picoscope to do it, so that we can see the actual square wave. You could do this with a DMM, you could do this with a test light, but not nearly as accurate as what we're going to do with the picoscope. And obviously, the fact that they're using a scope in this class makes me very happy. It gives me hope for the future that they're producing technicians that will have that technological capability, because you have to have a scope in today's vehicles. All right, now, this is a ground side or a pull down, because we're pulling down to ground when we close the switch. What did this guy call it? A low side or a low side? Either of these terms mean that our switching is on the ground side here. Now, that is going to be opposed to a pull up or high side or power side switching, as I call it. And that is going to be where this is essentially reversed. The PCM will be on this side of the device, and I've never seen a fuel injector that does this. I actually haven't seen too many things that do it, and the reason is because it's safer for a PCM to be on the ground side than the power side, because in the event of a short or something like that, if the wiring shorts out to the frame or short to ground or something like that, you're actually far less likely to blow out the PCM. That's a lot less likely to happen if you're switching on the ground side than the power side. So it's going to be a little challenging to find something like this, where we have our PCM here on this side, and our battery is going to power the PCM. And then we're going to have a switch here in the PCM. Technically, the switch is actually going to be a transistor, but we're just going to make a switch symbol here to make it very simple. And we've got positive here, and then this is going to go to some device that most likely is going to be permanently grounded. And here we see, to activate this device, when the PCM turns on and off and on and off, it's turning the power on and off, on and off, on and off, not the ground. And that's why this is a, what does he call it? High side, pull up, positive side switch, whatever it is. So that's something that I'm going to admit may be a little challenging for us to find. This is going to be very easy. We can go ahead and do this right now. So let's take a look here. Okay, this one here, measure the waveform of a low side driver controlled output using the picoscope. Let's do that first. That's going to be really easy. The high side, I'm going to have to find one. All right, this is going to be super easy on this car. We've got fuel injector right here. All right, and we've also got one here and here, probably off the camera. And I'm going to cheat just a little bit here. We see there is kind of a brown, maybe yellowish wire. This car's really like 20-something years old. It's probably why I got that voltage drop on the lights. But we've got, I guess it's a brown wire here, brown wire here, brown wire here. However, the second wire is different on each injector. That's telling me, because this is ground side controlled, the same colored wire is going to be a power feed. It's the same power feed to each injector, and the other wire is going to be the ground side control. So since we're looking for ground side control, we want to tap into this ground side wire. This is very important to know because we need to see what happens if we do this backwards. Okay, so throughout this video, I've constantly been asking, okay, in this situation, what would the voltage be here? Or what would the voltage be here? What would the voltage be here? This is the reason why I was doing that. There was always method to my madness here. The reason is because you have to understand where the voltages are going to change, because that's where you would have to hook up your picoscope or whatever your measuring device is. If you did not understand that concept, you are probably not going to set up correctly. We know we're going to have our picoscope here, and the picoscope, we're just going to use one channel. It's going to be very simple. Picoscope essentially is like a DVOM, right? It's just a scope is a very, very, very fast DVOM, and it's going to measure voltage. And what we are going to do, we need our red here. We're going to have a red lead and a black lead, and we need to know where we're going to put these leads. In the case of this particular application, we can just very simply do what would seem intuitive, and we can put our red lead here and our black lead here. Now we know this works because no matter what, all the time, we're always going to have 12 volts here, and here we are going to have voltage depending on whether that switch is open or closed. Right now, we would have 12. Close the switch, we now have current going through. When you have current, you will have the voltage drop across here. That should drop to 0. So on our scope, when the switch is open, we're going to be measuring 12 versus 12. We're going to have nothing, however long that is. That's going to be for the majority of the time. Remember, the fuel injector is going to spend most of its time being off as it turns on briefly, and then it's got to wait for all the other cylinders to have their turn, and then it comes around again, turns on briefly. So we're going to have very brief on times. So it's going to be off for quite a while. Then it is time to fire that injector. And now we're going to have 0 volts on this side. 12 versus 0, we're going to read 12. Our scope here is now going to read 12, and it's going to read 12 for a very, very brief period of time. As you know, a fuel injector is on in the millisecond range. And then the switch is going to open again, which means we're back at 12 volts here. 12 minus 12, 0, and we're going to see this over and over and over again. Now, the reason this is important is because sometimes you run into things where it's very hard to access the connector. The other thing, it is very, very important to realize that if these are close together, and we cross our pins with our back probes up here, well, now we have basically destroyed the computer, because now what's happened is we have our current going through here, but instead of going through the coil, like right now we're safe because the switch is opened. But when that switch closes and we put current through, that current is not going to go through the coil, which is the load in this system. That current is going to go through our crossed pins, which has no load. That's a short circuit. It's going to fry this computer. So setting up this way is really not the best way to do it. You can do it if you're very careful, but it's probably not the best way. A better way to set this up that's much more safe and professional, remember you guys in the class are going to be professionals, right? Will actually be to set your positive lead for your scope on the ground side over there, and then your negative you just put to any chassis ground. Now your leads are far apart as possible. There's no chance of you crossing them up by accident and shorting out your PCM. Now, this is why it's really important. What would happen if instead of this, we did what would seem to be the intuitive thing, and we take our positive lead and we put it to the power side of the injector? What are we going to read on our scope here? Well, we are going to always, no matter what, read 12 volts. It's just going to give a straight line at 12 volts. Why is that? Because of what we talked about all through this video. It's always 12 volts here. It's 12 volts anywhere along this part of our circuit. The only change with 12 and 0 is on this side as the switch opens and closes. If this switch closes, again, we will have 0 volts here. We still have 12 volts here, whether the switch is open or closed. That's where we're measuring. We're always going to have 12 volts. That's why it's important to understand why we want that lead to be on this side, because we know that's the side that's going to alternate 12 volts or 0, depending whether our switch is open or closed. Makes sense now? So let's go ahead and do that. We're going to go to channel A on my picoscope here, connecting to positive and negative. I'm going to take my negative probe, and hopefully my battery's charged up enough here to start the car. Take my negative probe, I'm going to go over to battery negative. We'll just use this convenient ground right here. All right, my positive probe, we are going to go on the ground side here. That ought to do it. Okay, that's making connection. Again, we want to be very careful we don't have our wire running against anything that's moving in the vehicle, that we don't cross up with anything. Looks good. Let's hook up to the computer. All right, now we are going to run into one small issue here, and that is almost certainly they're going to be using Picoscope 7 software in a automotive diagnostics class. I actually have a compatibility issue with my particular computer where I cannot run Picoscope 7. So I have to still be on Picoscope 6. It's actually easier to set up in Picoscope 7, but you'll have a totally different interface here. The main thing is we just need to set our time frame and our voltage scales. Now, we also know, if you watch this channel, we're going to have a little surprise. We expect the voltage is going to be 12 volts, on or off, on or off, on or off, 12 volts. That's actually not going to be the case here because, again, this is a solenoid essentially. And we know when the solenoid turns off, it's going to actually generate a voltage from the collapse of a magnetic field in its own. So we're actually not going to see quite what we normally expect with just a simple on-off like I showed on the board. But we are going to still see ground side control here. All right, so I'm going to start off at 20 volt, but it's most likely going to be more than that. Our time frame, let's set like a 500 millisecond right now. All right, let's go ahead and start up. As we see, we are over 20 volts there. If we narrow our time frame in, we can see a typical solenoid signal. Get a couple of them on there. That's an injector turning on and off, on and off, on and off. You see the on time is very minimal. All off time, then it's on again. We can trigger this. All right, so we don't get exactly a square wave here, again, because of the effect of the solenoid. But if we expand this out, this right here is actually our ground side control. This is the injector turning on, and then it's turning off right here. When it turns off, that's when we get our spike. It's very similar to an ignition coil, but we are seeing ground side control here in what is essentially like a dwell time. Our on time is about a couple of milliseconds if we look on our scale down here. All right, now that leaves us with the high side driver control. And on this one, maybe we'll find something with a little bit more of what we expect with the typical square wave, but we did achieve an objective. We wanted to find a low side driver controlled output using the picoscope. We did that. All right, let's see, high side driver controlled output. Let's take a look at a wire diagram, see if we can find one. All right, so pulling up wire diagram here for that first vehicle because the engine will run a lot quieter. It's a little bit loud with my Trans Am there. And we probably might do better off maybe if we looked at a power distribution diagram, but I just want to look through for anything. How are we going to know, first of all, if we find something even that is power side switched? Well, one of the things is that it's going to have most likely a constant ground, and it's going to be some kind of device that's going to be powered through the computer if it's always grounded. So I'm kind of more looking on the name of the device because I just happen to know which ones are more likely to be. So let's see what we may have here. Okay, so one thing, this car has variable valve timing, and those sometimes are controlled through power side switching. It's also a matter, I want to find something that's easy to get to, but I'm kind of liking this position actuator for the intake camshaft. So let's see if this is power side control or not. If we highlight our wires here, we go off the screen to 10 and 12, it looks like. We follow along. Okay, so one of them branches off and we've got our cam phaser control. Okay, so I'm kind of liking that. That means if our other wire, which is here, if this wire goes off to a ground, then we've got a power side controlled solenoid there. So let's follow 14 off. Okay, and that does go to a low ref. A low ref is actually a ground. That's a term for a ground in the computer. So actually we can use that. The intake cam position sensor. Let me go check and see if that's easy to access. All right, no such luck, but generally those VVT solenoids are power side controlled for whatever reason. So if you are working on a car that has one easy to access, there you go. We want to try to find something a little bit easier. Let's go back. It's too bad that that's hard to access because that would be nice. But also the other thing is that it's a solenoid. It's not going to give us the real square wave that I kind of want to see. I want to find something that's also going to give us that nice square wave. Oh, well, actually, this may be cheating a little bit, but the ignition coils, this kind of does everything that I want because technically, I'm going to argue it's power side switched, but it's a little bit iffy because it's power side switched through a transistor, which I still believe is power side switched. And it would give us that real nice square wave that I think we kind of want to see. But the thing is, the way these injectors work ignition coils. The way these ignition coils work is that there's a lot of wires in these ignition coils here, but we've got a constant power, a constant ground. The switching is done using a transistor inside the coil, and that switching is done by putting a small power from the computer into the base of the transistor. So I'm going to make a call, because this is my video, that is power side switch. It's not really power side switch, but we are putting a power into that transistor from the PCM. That is a controlled power switching. I don't know that that really qualifies, but it's going to give us a really cool square wave. And also the main thing is it's very easy for me to access. I think we're going to do that. Let me see if there's any other possibilities that'll be a little less controversial. But the good news is I don't have to worry about failing this class. You have fuel injectors. We know those are ground side switched. Want something regularly controlled by a driver. Yeah, I really think we're on the right track. Let's see, we got one more page here. Let's just check this page. By the way, I hope you're paying attention to some symbols. Here's one. Here's a potentiometer symbol right here. This is a very common one. We have essentially a variable resistor. This is a fuel rail pressure sensor. Obviously, fuel rail pressure can vary a little bit. As pressure in the fuel rail increases, there's a sweep here, this little arrow, that will move up or down a variable resistor. Remember our variable resistor symbol. This symbol right here, you take one look at that, I see 3 wires coming out of it. My first instinct, potentiometer. So there's a symbol there. The heater on the oxygen sensor may be power side. No, those are usually ground side switch too. I know that as well from a previous video where we had a heater circuit issue. Let's see, map sensor. Yeah, let's see, the throttle body. No, the knock sensor. Now that's an interesting one because the signal comes from the knock sensor. But by the way, notice also this is another pretty common symbol. That's going to be a piezoelectric crystal symbol right there. Basically, vibration of this device activates that crystal and it produces a voltage. That's not a controller power side switching thing though, so that doesn't count. Notice our symbol for the motor here. Switch symbol here. Another symbol too, just probably will come up. We also have a symbol here which means a junction, where basically we see these wires kind of go over each other and under ones. But if you have a dot there, I hope you guys realize that means that this wire is actually physically splitting off into 3 other directions besides this one. All right, I have made my decision. We are going to do the ignition coil. So let's go ahead and set up. First of all, we need to identify the wiring. Okay, so if we look at our ignition coils here, and I'm not sure whether we've got like 1, 2, 3 in the front or 1, 2, 3 more in the back, that would be harder to reach. The ones in the front are super easy. But it shouldn't really matter because we can just look at this and we see on this ignition coil right here, whatever one it is, I don't care. We've got black, pink and black, light blue and white, brown and white. If we look at this ignition coil, it's actually number 6. This is number 4. Again, I don't care. We've got black, pink and black, dark green and white, brown and white. The wires are exactly the same except for one of them. And that wire that is different, that is going to be the input signal, the positive voltage input signal into that coil to turn it on. That is going to be controlled by the computer. This one is light blue and white. This one's dark green and white. This one's brown and white. Wait, how can it be brown and white? That's not, oh, okay, orange and white. And on this one, it's switched up a little bit. The brown and white is a constant on all of them. On this one, it's a dark green, so it kind of moves the position. That was a little tricky. But the different colored wire, let's just make sure of that. Let's follow a different colored wire, and let's follow that. And this is going to go into ignition coil 6 control at the PCM. Not sure why these are still highlighted. Oh, it goes right there, and there it is. Injector 6 control, right from the PCM. Okay, that's what we're gonna do. All right, so we'll access this one here so it's a little bit easier. Let's see, all of these have a pink and black. We know all of them had a brown and white. This right here is a green with a white. That is, I don't know what color that is, but this one here is a red. So this wire here is the one that's different. This third wire over is different on every one of these. That is going to be our signal input. That is going to be a signal in, positive voltage from the computer. I am calling this a positive side switching. I don't care because it's easy. All right, so we're going to probe this. Okay, let's see if this will work. I've got my positive lead from channel A right into that signal wire that I know is going to give a input signal, a positive input signal from the computer. The negative lead for my picoscope is on battery negative. We've got a 10 volt scale. I anticipate that actually. I'm going to just change this to 5 volt because this isn't going to be 10 volts. This is going to be probably less than 5 volts. We just need a signal in there. It's not powering the coil or anything. And then I'm going to start off with a 500 millisecond time frame. So remember those settings for if you decide to do this. All right, let's start the car. We should get a square wave. All right, and that is going to be a square wave. Okay, so we can see that we've got, yeah, maybe the 5 volts was a little aggressive. Some of these are just a bit over. If we narrow down, probably first we should set a trigger here. Be a little easier to see. And then if we split out our time frame, there's a square wave right there. Now we can see multiple of them if we expand out. That doesn't look good there, but I kind of like that. Okay, so there's several signals. You see that we have very, 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 very short on times here as the ignition coil is firing and then waiting its turn again and then firing for, again, just a split second that we get that signal to turn it on. Right in the middle there. All right, I believe that qualifies as a positive side control from the PCM, controlling that ignition coil on and off. All right, hopefully this was helpful. Good luck to whoever is watching this and has some electrical tests in their automotive programs. Really hope this helps you out. All right, we'll see you next time.